Let's go through equals 363. Maximal sum of rectangle no larger than k. So it gives us a integer matrix. And let's find the the which a rectangle which has a sum not larger than k, and we want to find the maximal sum. Um, So it says that it's granted that there will be a rectangle with sum no larger than k. So for this question, we can use a prefix sum way, right? And we pre-process to get a prefix sum which has m plus 1 multiplied in m plus 1 integer array. And if we do this way and we iterate every right bottom point and also iterate every up left point, so that we have for loop, right? So that will be O n square m square time complexity for this kind of approach. But let's see, it has m and small equal to 100, right? So it is possible those kind of time complexity will be, it will be 10 to the power 8. It's possible it will be TLE. So can we do better for better time complexity? Actually, we can, right? The way we do better time complexity is that what we do is that we iterate uh, every upper row, right? We call starter row, and also the end row. So there are two for loop, right? So depend on which one is bigger, M or N, right? Um, for example, if N is greater, we just iterate start row and end row. Of course, there's another approach is that we just iterate start a column and end a column, right? But this question didn't say which one is better. So let's just iterate, didn't say which M or N which is greater, right? So we just iterate, use two for loop to iterate the starter and the row. So the thing is that we want to compose an array, right? Array for column from 0 to n minus 1. So the sum in this range, right? So how can we get this kind of array in some kind of efficient way, right? If every time we iterate this and we sum those kind of up, it will be very time consuming, right? So we can actually do a pre-processing. For every column, we have a prefix sum, right? Then for every column, we have a prefix sum. Then every time we iterate this kind of start row to end row, we are going to and we're going to have the um, have this kind of array, right? Just the sum of this array in for example, we fix this kind of row and column, and that is we just iterate these kind of columns. This style and row, right? We just iterate from this start to end. Use for everyone, we use a prefix sum to calculate the sum of this, right? So this is every approach to get the prefix sum to have the array we call compressed array, right? Compressed array in O n approach, right? This compressed array is just the sum in this range, right? So for example, this is let's take an example, right? So for example, we have 2, 3, 4, 5, and 3, 2, 3, 4, and 5, 4, 1, 2, right? So for example, our start row is here, and our end row is here, right? So if we iterate, this is start row, this is end row. So we can use an ON approach to get, for example, get the result. This kind of array to be 7, 7. What is this? This is okay. Let's say this is 2, this is 5, 6, right? We can just have an ON approach have 7, 7, 0, 6. So this is we iterate to start row and end row every time we get a compressed array, right? Which means the sum for this kind of range, for this range, right? And for this kind of for our compressed array, what we want is that we want to look for the what we want is for this kind of compressed array, we want to find the subarray, right? Smaller than k, and also the closest smallest to k, right? So how can we do that? We can also use another prefix sum for this, right? For example, we have array, right? Compressed array. We want to find the largest subarray smaller than k. Then what we do is that we can put this kind of prefix sum into a tree set, right? Tree set. And every time we iterate to a prefix sum, we just trying to have this kind of current prefix sum minus k, right? And we are going to find in this set a Selling result for this kind of things, because for this Selling one, that will be that is the it the Selling one will be the largest close to the Selling one is we are going to up, right? So that means the current minus this will be smaller than k, right? So in this case, if we find a Selling result of the previous from the previous tree set, then current minus the Selling result will be one of our candidate result, and we compare this result with global result, right? So doing like this, the time complexity will be this row will be m squared, right? And for this kind of column, we compose a compressed array that is an ON, right? But we iterate this one. We use a tree set, and after we've composed, we do a separate approach. That is for every prefix sum, we want to find the Selling result, right? So that is tree set is n, it is the log n operation, but we iterate the compressed array, so it is n log n, right? So the total result time complexity will be O m squared n log n time complexity, right? So this is when if n is greater than m, we do like this approach, right? So we compress the column, get a prefix column sum. And but if for example, if m is greater than n apparently what we want is we'll get n square m log m time complexity will be better, right? So what we do is that we do prefix sum in a row level, right? Do similar approach. So after this analysis, we can write code. So we are going to have in M equals matrix total length and N equals matrix 0 dot length. We are going to have something called a prefix column sum. So what does this mean is that for each column, we get a prefix sum, right? So that is m plus 1, right? We know prefix sum will have one more index, and there are n columns, right? So what we do is that for every column, j into j equals 0, j is smaller than n, j plus plus. Then what we do is that for int I equals 1, I is smaller than m plus 1, I plus plus. So we're going to have prefix column sum I j equals prefix column sum I minus 1 j and plus matrix I minus 1 j, right? Then what we do is that let's have a int result equals integer dot mean value, and we iterate the two start column and the end column, right? For int end column and row, right? And row equals 0 and row smaller than m and row plus plus, and we're going to for int start row equals 0 and start row smaller equal to end row start row plus, right? Then we are going to have a compressed array, right? Compressed array. We will be we just use a compressed column sum, right? So that is well, let's get this one for everyone. We get this kind of get a compressed array first. Then we for every column, right? We get a we fill the compressed array. Then that is compressed array J equals prefix column sum, right? And row plus 1 J minus prefix column sum star row J. So we have this kind of compressed array, right? So let's use a tree set to put the prefix sum into it, right? Because we want to find the closest one, which at which the current minus the previous one will be smaller than k. So we use a tree set. Otherwise, we need to put into collection and sort, right? In the do binary search, we set equals new tree set. So what we do is that let's have a tree for prefix sum. We add and 0 at the beginning, right? So what we do is that let's have compressed prefix sum, right? Let's set this one as 0, and for int j equals 1, j is smaller than n plus 1, j plus plus, right? Then what we have is compressed prefix sum the plot equal to compressed array, G minus 1. Then we have an integer v equals preset. We get a selling compressed prefix sum minus T. Then if this doesn't equals none, right? Because it's possible there is no selling new selling records in the tree set. If it's not equals none, we have result equals next dot max result and a compressed prefix minus 3, right? And also we need to have the tree set at this compressed prefix. And then in the end, we just return result. And the Python code will be very similar. So we are going to have, let's get a equals this length matrix and the length matrix there, right? So we're going to have prefix column sum equals let's say this one multiplied by n for this one in range m plus 1. Then we're going to have for j in range n, we're going to have for I in range from 1 to m plus 1, right? We're going to have prefix column sum I j equals prefix column sum I minus 1 j and plus matrix I minus 1 j, right? Then what we do is that for let's have a result equals float minus IF. Then we're going to use for any row in range and for start row in range and row, right? Then what we do is that we're going to have for we're going to create the compressed array equals this one multiplied by n, right? So let's fill the result Rj in range, and we're going to have compressed array j equals prefix column sum and the row plus 1 j minus prefix column sum start row j, right? Then let's include the sorted set for from sorted containers import sorted list. Then what we do is that we're going to have sorted list, sorted prefix, right? Prefix equals sorted list with a zero index. So we have compressed the prefix sum equals to zero, right? Then what we do is for j in range and we have compressed prefix sum plus equal to compressed array j, right? Then we're going to have index equals sorted prefix it by binary search sector left compress the prefix sum minus k, right? Then what if index is smaller than length sorted prefix, we're going to have result plus max result compress the prefix sum minus sorted prefix index, right? And also we need to have a sorted prefix add compressed prefix sum, right? And in the end, just return result. Sorted container, sorted containers. Let's take a look. J minus one prefix goes m plus one, so sorted Xi plus compressed next is equals sorted by select minus k. If this one result equal to sorted index. Mm. Should a plus one enter with the plus one. Okay, so this will be the Python code.